Welcome to Dia and Daniel Presents, the exciting season premiere of The StereoBachelor, the place where true chemistry is forged starts right here, right now. Here before us we have Bachelor number 1, 2-bromo, 1-chloropropane, and he is here to search for his molecular soulmate. Well, he's certainly come to the right place. First, let's look at the qualities that make him unique. He possesses one asymmetric carbon, which, if you've forgotten, is a carbon atom attached to 4 different types or groups of atoms. To demonstrate, the following is an asymmetric carbon because it is attached to a hydrogen going away from us, a bromine coming towards us, a CH3 molecule to the left, and a CH2Cl molecule to the right. These are 4 distinct groups of atoms. So, what do asymmetric carbons do? The answer is to destroy planes of symmetry. For example, the following molecule has no asymmetric carbons. There is therefore a possible plane of symmetry, like this one denoted by the dotted red line going right down the middle. We call these molecules achiral. But molecules with no possible planes of symmetry, like our bachelor here, are considered chiral. With that explanation out of the way, let us meet our first female candidate, 2-bromopentane. It seems that things between them aren't going to work out, and I wonder why. The answer lies in their molecular compositions. Our bachelor here has a molecular formula of C3H6BrCl, while our female candidate's molecular formula is C5H11Br. They're completely different compounds. No wonder they didn't match together. Well then, let us bring on female candidate number 2, 2,2-bromochloropropane. They seem to be much more friendly towards each other. I think it's because they have identical molecular formulas. They're both C3H6BrCl. But wait, things are still going awry. What's going on here? Ah, I see. They are constitutional isomers of each other. Constitutional isomers are molecules with the same molecular formula, but different chemical structures. Our bachelor's chloro group is on his first carbon, but he's going to have conflicts with a partner whose chloro group is on her second carbon. I hope the next candidate is going to work out. Let's bring to the stage 2-bromo, 1-chloropropane. I can start to feel the electricity in the air. They're really liking each other, I can tell, but something is still missing. What is it? Can it be that they are the same molecule? Can it be? That's exactly right. Our bachelor here is looking for a partner in life, but not another one of himself, which is why this is not going to work out. That is because if we rotate the carbons by 60 degrees, we would find that the female candidate is indeed identical to our bachelor, like illustrated here. Just as our dejected bachelor is about to give up his search for his life's greatest love, female candidate 4 shows up. 2-bromo, 1-chloropropane. The two share an immediate affinity for each other. It's almost as if they're mirroring each other. Can it be that our bachelor found the elusive, once-in-a-lifetime enantiomer of himself? The perfect partner that a molecule can wish for? Well, let's see. We describe enantiomers using the R/S notation, whereby we label each asymmetric carbon as either S for sinus or R for rectus. To do so, we first label all the molecules the asymmetric carbon is attached to in order of size. The largest atom/molecule, like the bromine here, receives the lowest notation in order, 1, 2, and 3. And similarly here, 1, 2, and 3. To determine R or S, we should point our thumbs in the direction of the smallest molecule connected to the asymmetric carbon, which is most likely going to always be a hydrogen, and see whether your left or right hand best fits the pattern. For our bachelor here, you would find that the right hand best fits the pattern, and for our female candidate here, we would find that left hand best fits the pattern. And that's how we determine that they are enantiomers of each other, and that's why they're perfect for each other. In case you're wondering, if a molecule has 2 asymmetric carbons, it is possible to have what's called diastereomers, where molecules with only 1 asymmetric carbon's R/S notation reversed, like the following example. This one here has 2 R asymmetric carbons, while his diastereomer has 1 R and 1 S asymmetric carbon, which is why they're diastereomers of each other rather than enantiomers of each other. In order to be enantiomers of each other, there has to be S and S. One last thing. There are such things as mesocompounds, however elusive they may be, which contain asymmetric carbons but do not have enantiomers. For example, here you have a 1,3-dichlorocyclohexane. This one is an R asymmetric carbon and an S asymmetric carbon. But we would find that if we create the enantiomer of this molecule and have an S and an R, you will find that they're actually identical, because you just have to flip this molecule. They're one and the same. Which is why, for these poor meso compounds out there, they're going to have to love and learn how to love themselves. The end.